Hello guys, I am Shubham Das from the Blockchain Century and I hope you all are doing well, and today's video is going to be about the structure of block in a blockchain. So make sure you like and subscribe to the YouTube channel to get more knowledge about blockchain technology. So let's get started. Okay, so what is a blockchain? A blockchain is a digitally distributed, decentralized public ledger that exists across a network. So, in simple words, the data records are stored in every computer connected with the blockchain network, which makes it transparent to all and immutable among the network. Okay, so now the structure of a blockchain within the network. A blockchain is a linear chain of block like a linked list where each block is connected linearly by storing the hash of the previous block. So, what's a hash? So a hash is like a digital fingerprint, like every one of us have a unique fingerprint. Similarly, the block also consists of a unique fingerprint known as the hash. And here you can see that if every block consists of its hash and the hash of the previous block known as the previous hash. And please note down one thing that the first block created within the blockchain is known as the Genesis block, and it just have a null value in the previous hash. Like as you can see here that it consists of a previous hash which is of a null value, and it is because there is no block before the Genesis block. Also, this is the first Bitcoin hash you can see here. Okay, so moving to the next slide. Okay, so what is a block? A block is a container data structure which contains a set of confirmed transactions. So a block could contain different informations, and a chain of these blocks evolved into a blockchain as long as it links one and the other. A block are stored on the hard drive of a many miners spread across the globe as peer-to-peer network. We will talk about the types of miners in our upcoming videos. And after that is in Bitcoin algorithm, a block is created in every 10 minutes. Also, block mostly consist of transactions, timestamp, block identifier, nonce value, previous block hash, and other informations. So we will dive deep into this topic. Okay, so moving on to the next slide. So structure of a block. Each block consists of a block identifier, block header, and a body. So what's a block identifier? A block identifier is a part of the block through which we can identify a particular block, and it consists of a block hash and a block height. And a block header consists of several fields like previous block hash, timestamp, nonce, difficulty, and Merkle tree root. A block body also consists of transactions in the form of Merkle tree. And note one thing that the block header is of 80 bytes, whereas the average transaction is at least 250 bytes, and the average block consists of more than 500 transactions. So you can say that a complete block with all the transaction is therefore 1000 times larger than the block header. Okay, so moving on to the next slide. So this is a block structure. Okay, so you can see this block. It consists of three parts: block identifier, block header, and block body. So a block identifier consists of two things: block hash and block height. And similarly, the block header consists of five things: previous block hash, timestamp, nonce, difficulty, and a Merkle tree root. This Merkle tree root comes from the block body, which consists of a Merkle tree. We will come into these things. So let's start with the block identifier. Okay, so let's talk about the block hash first. To identify a block, we need to have a cryptographic hash, which is a unique digital signature. This is created by hashing the block header twice with the SHA-256 algorithm in case of Bitcoin blockchain. And another way to identify a specific block is in the blockchain is the block height. This is the position of the block in the blockchain. So let's see them one by one, but first let's see what is this SHA-256 algorithm. So SHA-256 is a hashing algorithm. So what's a hashing algorithm? A hashing algorithm is a cryptographic hash function It is a mathematical algorithm that maps data of arbitrary size to the hash of a fixed size. So here, as you can see, that we can provide some data in SHA-256 like documents, audio, video, pictures, etc. And it will convert it into a 64 hexadecimal character where each hexadecimal character is of 4 bits. Therefore, 64 into 4 equal to 256 bits. So that's why it is known as SHA-256. Secured hashing algorithm 256. Okay, so now you can wonder what is a hexadecimal character. Decimal system contains 16 sequential number as a base, including 0. As you can see here, the first 9 numbers 0 to 9 are the same ones commonly used in the digital system, and the next 6 two-digit numbers like from 10 to 15 are represented by the letters A through F. So, like here, from 0 to 9, it is same as the decimal number, but from 10 to 15, it is represented by the alphabets like A, B, C, D, E, F. And after then, you may wonder why do we need a hexadecimal number? So hex numbers are compact and they use less memory, so more number can be stored in the computer system. So their small size also makes input output handling easier compared to the other numbering formats. As we have learned about the SHA-256 algorithm, let's learn the hashing first. So block hash or cryptographic hash. The primary identifier of a block is its cryptographic hash, which is a digital fingerprint made by hashing the block header twice through the SHA-256 algorithm. The resulting 256-bit hash is called the block hash, but it is more accurately the block header hash because only the block header is used to compute it. And thereafter, the SHA-256 is secured hashing algorithm 256. I told you this thing earlier. So what happens is you can see this block header. It consists of previous block hash, timestamp, nonce, difficulty, and Merkle tree root. So all these things are put into the SHA-256 algorithm, and after that the SHA-256 algorithm converts the whole thing into a 64 hexadecimal character first, and after this the 64 hexadecimal character again is put into the SHA-256 algorithm, and then it converted into a 64 hexadecimal character again. So like this, the block header is hashed twice with the SHA-256 algorithm. Okay, so there are some requirements we want the hashing algorithm to fulfill. So these are one way, like the data can only be converted into encrypted data, and the encrypted data can't be converted into the original data. Like say for example, if we put 1234 to the hashing algorithm, it should produce ABCD, and the ABCD should not be converted into 1234 again. Like the reverse is should not be possible. And the other one is deterministic, like the data should produce the same encrypted data every time. Like if it is producing 1234, we are giving 1234 and it is producing ABCD, then every time it should produce ABCD whenever we give 1234. And it should not be like that if we are giving 1234 and it is producing DEFG. It should not be like that. And the next one is fast computation. Like it should convert the data into encrypted data really fast, otherwise it will take a long time to make a single block, and then the blockchain won't be a scalable technology. And the next one is collision resistant, like no hacker can decrypt the encrypted data easily. And then the next one is avalanche effect, like if we can even change a single bit of the original data, then the whole encrypted data outcome should change. Like here, if we change a 1234 to 1235, then the whole outcome of a ABCD should be changed to EFGH. So it is like that. Okay, so now let's see these things with a practical example. So here we are going to see how SHA 256 is fulfilling all the 5 requirements. So the first one is one way. Like as you can see, the data is given here, and it produces a hash of 64 hexadecimal characters, and you cannot reverse it, like you cannot convert the hash into the data. And the second one is deterministic, like every time you give this thing, it will give the same outcome. Like here I am cutting this one, this transaction, and the hash changes, but whenever I give the hash again, sorry, the transaction again, it is giving me the same result. So it is deterministic. And the other one is fast computing. So here, as you can see, it is computing with the outcomes of this SHA-256 really faster, like here. And the other one is collision resistant, like no hacker can create their information from the hash. And again, the one is avalanche effect, like here if I change the single bit from the data, like here I am converting this 4 into 5, then you can see the whole hash change immediately, and everything is different in this hash. Like you can see the 4 here and the 5 here. Okay. Okay, so now let's talk about block height. Block height refers to a specific location in a blockchain, measured by how many confirmed blocks come before it. So as you can see here, here is a Genesis block counted as block 1, and every block after that will be counted sequentially. Like here is block 1, block 2, block 3, block 4, block 5. And if one block is added after block 5, it will be considered as block 6. And remember one thing, that block height is also known as block number. Okay, so now let's move to the next slide. So the next one is block header. The block header consists of three sets of block metadata. First, there is a reference to a previous block hash which connects the block to the previous block in the blockchain. The second set of metadata, namely the timestamp, nonce related to the mining competition and difficulty. The third piece of metadata is a Merkle tree root, a data structure used to efficiently summarize all the transactions in the blockchain. So let's see all of this one by one. So the first one is the previous block hash. So each block header consists of the previous block hash, which ensure that nothing has been tampered with as new blocks are added. Cryptocurrency blockchains are hashes to secure information and make the ledger immutable. So as you can see here, here is a block 1, block 2, block 3, and each block consists of the hash of the previous block. But the Genesis block do not have a previous block, as it is the first block and there is no block before it. And here in block number 2, you can see the previous hash consists of the hash of block number 1, and similarly in block 3. Okay, so now let's see these things with a practical example. Okay, so here, as you can see, here is a blockchain with some blocks from block 1 to block 5, and every block consists of a previous hash and the hash of its own. And the make sure that you notice one thing, that the Genesis block only consists of its own hash, and the previous hash only have some null values. So it is like that. And whenever you change the data of a one block, it will change the hash of that block, and similarly the hash of the previous block will also change. And after that, if the previous block hash will be changed, then the hash of the same block will also change. Like let me show you. I am inserting some malicious data, and as you can see, as I have changed some data, the hash of this block have changed. And similarly for this block, block number 2, the previous hash of the block also changed, and the hash of this block also changed. So like that, every block after block number 1 have changed. So that's why blockchain is so much secured, because you can't tamper with the data. If you tamper with the data, then the hash of the same block will change, and the same will goes with the previous block. Okay, so the next one is timestamp. So the timestamp is a small data stored in each block as a unique serial, and whose main function is to determine the exact moment in which the block has been mined and validated by the blockchain method. So here you can see that the block header consists of this timestamp, and the timestamp is stored as a unique timestamp in blockchain header. So what is a Unix timestamp? So let me show you. So this is the Unix timestamp till now. So the Unix timestamp is a way to track time as a running total of seconds. This count start at the Unix epoch on January 1st, 1970 at UTC. Therefore, the Unix timestamp is a merely the number of seconds between a particular date and the Unix epoch. And this value is running continuously from January 1st, 1970 till now. So talking about the nonce, a nonce is a random 32-bit number that the miners use as a base for their hash calculation. The miners compete with each other trying to guess a valid nonce as they attempt to calculate a block hash. So whichever miner gets the correct nonce will be add the block to the blockchain. So so initially what happens is that the blockchain algorithm will produce a target hash which will be between the maximum value of the hash and the minimum value of the hash. So how you will consider it as minimum and maximum? So here as you can see that the decimal value of the minimum is 0 and it is represented as 0 in a hexadecimal format, and similarly as the hexadecimal value goes up to 15 and it is represented by f, so f is the maximum value, so it will be FFFF. Also, the blockchain algorithm constitutes a target hash, and the miners need to change the nonce to give a hash which should be equal or beneath the target hash. So let's say a miner constructs a block and he want to add it to the blockchain. So for that he have given a nonce which is completely random 32-bit number. So what the nonce will do is that it will produce a block hash, and the block hash will be somewhere in this space. And let's say it is above the target hash. So the blockchain algorithm won't consider the hash value and it will be rejected. Like as you can see here that the nonce value is 13343 and the hash produced by it is above the hash target, so it won't be considered. So again, this time the nonce is 10035 and it produces a hash which is also upper than the target hash, so this one will also be rejected and the block won't be added. So now this time the miner constitutes a right nonce, and after that the hash value is beneath the target value, so it will be considered and the hash will be taken as the hash of the block and it will be added to the blockchain. Okay, so moving on to the next slide. So mining difficulty. Every block has a mining process by which miners can add blocks in the blockchain. An algorithm regulates how difficult it is for the miners to mine a certain block. The difficulty is known as mining difficulty. For mining a block, a miner must solve a complex mathematical problem by finding a valid hash. As the process progresses, the network adjusts the rate so that the miner finds valid hashes. So here you can see for Bitcoin, let's say the target hash is this one, and let's say the Bitcoin algorithm wants the target hash to be more difficult, so it decreases the target hash so that it will be more difficult for the miners to find the hash, the target hash. So each blockchain has its algorithm to regulate the adjustment. The algorithm increase or decrease the mining difficulty based on the rate at which the miners can mine a block. Okay, so I hope you understand this part. The next one is block body. A block body consists of transactions. Transactions are stored in the form of Merkle tree inside the block. The transactions are submitted and are picked up by the blockchain network and is inserted into the pool of unconfirmed transactions. So this pool is known as transaction pool or mempool. The miners on the network select the transactions from the transaction pool and add them into the block, and specifically into the block body. So moving on, and let's see how the Merkle tree works. A Merkle tree summarizes all the transactions in a block by producing a digital fingerprint of the entire set of transactions. The users can verify whether or not a transaction is included in a block. And Merkle tree are created by repeatedly hashing pair of nodes until there is only one hash left, which is known as the Merkle tree hash, which is present in the block header. And each leaf node is a hash of transactional data, and each non-leaf node is a hash of its previous hash. Muggletry are binary and therefore requires an even number of leaf nodes. If a single detail in any of the transactions or the order of the transactions are changed, so does the Muggletry root also changes. So let's see the structure of a Muggletry root. So here you can see here is a Muggletry which consists of several transactions T1, T2 up to T8, and these transactions are initially converted into a 64 character, and then they are again hashed together to produce a single hash. This is done by SHA-256 algorithm, and this process continues until a single hash is produced by all of the hashes, and this hash is stored in the block header. Now you may think that the Merkle tree are binary and therefore requires an even number of leaf nodes. So what if there is a odd number of leaf nodes? So you can see this case where it consists of odd number of leaf nodes. So what it have done is that it have conserved this H1 H2 and it took H3 H4 and it produced one hash, and this hash also taken the same hash from the previous one and it combined and made a single hash, and again these two hashes are combined to produce a root hash. So it is done like that. Now imagine a scenario where one hash is changed. Some hacker have changed a transaction in this Merkle tree. So here you can see the transaction is changed. Like previously it was T3, but now it is T9. So when the transaction is changed, then the hash of the transaction will also get changed. And similarly, all of the transaction after that will change the hashes. And at last, the hash of the root will also get changed. So when the root hash get changed, then what will happen is that the Merkle tree root will change in the block header. And as the block hash is created by the block header by putting the block header elements in SHA-256, then that's why the block hash will also get changed. So if the block hash get changed, then the previous block hash after the block will also get changed, and the whole chain will get collapsed. So for this reason, the transactions are irreversible and you cannot alter the transactions. So that's why blockchains are immutable. So that's all about today. I hope you like the video. Make sure you ask your doubts in the comment section.